Hi there. So today I'm going to talk about section 4.0. It's actually at the end of chapter 4. It's Exponent Skills Refresher. Okay, we're going to, in chapter 4, discuss exponential functions. But before we actually get into exponential functions, it's really important to refresh yourself on our properties of exponents. I have them already listed over here. My hope is that you're familiar with them. And what I want to do before I go through a bunch of examples is just go through a few of these with you to show you why they're true. For example, notice when you multiply two things with the same base, you add your exponents. When you divide two things with the same base, you subtract your exponents. And similarly, when you raise something to a power, raised to another power, you multiply your exponents. So we could just take a quick example of that. For example, what if I have something like x squared times x cubed? Well, x squared is x times x cubed is x times x times x, and I think if you look at this, we say, oh, that's the same as x to the fifth. Notice we multiplied two things with the same base, and lo and behold, we add their exponents. Okay? Similarly, suppose I have x squared and I cube it. Well, x squared is x times x, so I'd be cubing that. What does it mean to cube this? It means that I multiply that by itself 3 times. I can count up the number of x's I have, and notice I've got 6 of them. 3 times 2 gives me 6. Okay? Now, in a similar manner, I can look at things like, how about x to the fifth over x cubed? Well, x to the fifth is the product of 5 x's. X cubed is the product of 3 x's. Since I'm multiplying, I can cancel, and notice I'm left with 2 x's in my numerator. Okay? And 5 take away 3 gives me 2. Now, on the other hand, what if I have x cubed over x to the fifth? Well, that looks very similar, but now I have 3 x's in my numerator and 5 x's in my denominator. 1, 2, 3. So I've got a 1 and I've got an x squared here. Okay? Now, if I use that property that we just showed up here, we have x to the 3 minus 5th power, which is x to the negative 2nd, which we've seen is the same as 1 over x squared. The moral of the story, when you have a negative exponent in your numerator, you bring it on down to your denominator. Okay? And in a similar way, if you have a negative exponent in your denominator, in order to make him positive, you bring him up to your numerator. All right, one other thing I will show. What if I have x cubed over x cubed? Okay? Well, what do we know? We know that any number divided by itself is 1. So we know in the back of our heads that that's equal to 1. But using our properties of exponents, when you divide two things with the same base, you subtract your exponents, and so we get x to the 0 power. In other words, when you raise something to the 0 power, that's equal to 1. Okay? Now, one other thing that I would like to go through involves this guy here. When you're multiplying two things and you raise that product to a power, what this says is you can bring that power into each of them. For example, what if I have x times y cubed? Well, written out, isn't that xy times xy times xy? That's what it means to cube something. Now what we can do is we can use our commutative property of multiplication, which says it doesn't matter which order you multiply. In other words, we can get all of our x's together and all of our y's together. So that tells me I've got 3 x's, and then I'll put my y's together. But isn't that equal to x cubed times y cubed? Pretty sweet. Okay? Now, I want to contrast that with something else. Okay? The thing is, when you're multiplying inside and you raise that to a power, you can bring your exponent in. That does not work for addition or subtraction. Okay? And that's a really important thing to keep in mind. For example, if that did work with addition or subtraction, then what we would be saying is something like, well, 9 plus 4 quantity squared is equal to 9 squared plus 4 squared. We're going to see that we can have a big no right there. But check this out. Okay? Order of operations on our left side say that we do what's in parentheses before we deal with the exponents. So 9 plus 4 is 13, and 13 squared is 169. Well, if this was true, then we're saying that that would be equal to 81 plus 16, which is 97, and I think you'll grant me that those are not equal. Okay? It's so tempting to want to bring your exponent in when you're adding or subtracting, but it is just not a true statement. Okay? All right. So, what I would like to do now are go through some examples. You know, the properties of exponents, they're one of those things that once you play around with them for a while, you'll remember them. I will keep them listed right here for right now. And the first thing that I would like to do is contrast these two things. Negative 5 squared versus negative 5 squared. This looks very similar. The difference exists in the fact that the first one has parentheses and the second one does not. This is where it's really important for me to emphasize your order of operations. Okay, you always do your parentheses before you do your exponents, and you do your exponents before you do your multiplication. Okay? In other words, if I'm looking at negative 5, the whole quantity squared, I have to take into account my parentheses first. In other words, this second power applies to everything in my parentheses. So that's negative 5 times negative 5, which is a positive 25. On the other hand, notice there are no parentheses here. Okay, so what I do is I do my exponent before I do my multiplication, because this is essentially saying negative 1 times 5 squared. Okay, so here my exponent only applies to that 5, and I just have my negative sign hanging out in front. And here you get negative 25. The moral of this story is pay attention to whether or not you have parentheses. Okay? All right, so what I want us to do right now is evaluate a whole bunch of things, and we're not going to use a calculator. So, for example, what if I want to take the square root of 4 to the 4th? Okay? Now, I could compute 4 raised to the 4th power and then take the square root of that. But since I'm not using a calculator, I want to use my properties of exponents, if at all possible, so that I don't have to do too big of computations in my head. Okay? Notice here I've got 4 to the 4th power, but when you're taking a root, that's a fractional exponent. Our square root is raising it to the 1/2 power. Now I can use my properties of exponents that say when you raise something to a power, raise to another power, you multiply your exponents. And 4 times 1/2 is 2. And so we get 16. Okay? That was a nice manageable size number. Okay? What if we want to evaluate this guy without a calculator? Well, what's the issue here? The issue here is I have a negative exponent. Okay? It's considered bad manners in mathematics to have negative exponents hanging around. So our first goal is to write this with a positive exponent. Well, as I just said a little while ago, if you have a negative exponent in your denominator, in order to make him positive, you move him up to your numerator, and 7 squared is 49. All right, what if I have this guy? What if I have 16 to the 3/4 power? All right, again, we're not going to use a calculator here. What I would do is I would rewrite my 3/4 power in the following way. I would write that as 16 to the 1/4 power cubed. Okay, let's just stop a second and check that we have what we have is equivalent. Okay, again, when you raise something to a power, raise to another power, you multiply your exponents, and certainly 3 times 1/4 is 3/4. All right, so now we need to ask ourselves, what does it mean to look at 16 to the 1/4 power? Essentially what we're doing is we're taking the 4th root of 16 and then we'll cube it. Well, fortunately, this is something we can compute. The 4th root of 16 is 2, correct? 2 times 2 is 4, times 2 is 8, times 2 is 16. Knowing your powers of 2 and 3 can be very helpful. So we reduced what's inside our parentheses to just our lovely number 2, and then we cube it to get 8. All right, what if we want to look at this guy? Negative 8 to the, let's do this, negative 2/3 power. All right, the first thing that I would do is get a positive exponent. How do you make your exponent positive? What you do is you bring him down to your denominator. Okay? Notice that changed the sign of my exponent. It did not change the sign of my negative 8. Okay? Now, how would I proceed from here? I would follow along in a very similar manner as to what we just did. I would write that as 1 over negative 8 to the 1/3 power squared. No, there's a lot of parentheses, but I just want to keep this negative 8 all together. Okay? Now, what does it mean to take negative 8 to the 1/3 power? I'm taking the cube root. Now, I understand if initially you were taken aback that you have a negative here, but again, when it's an odd root, you can take that root of a negative number. Okay, so I claim, well, I'm asking myself what multiplied by itself 3 times gives me negative 8, and that would be a negative 2. And then we square it to get a positive 1/4. I think these are really fun. Okay, now what we're going to do is we're going to simplify radicals. Okay? So we're done dealing with just numbers, and now we're going to have a bunch of x's and y's and all of that fun stuff. Okay, so the first one that I'm going to look at is the following. What if I want to take the square root of, it doesn't really matter, x to the 8th? Okay, Well, isn't that equivalent to x to the 8th to the 1/2 power? Which gives me x to the 4th. Again, when you raise something to a power, raise to another power, you multiply your exponents. Now, on the other hand, what if I wanted to take the square root of x to the 9th? Okay, I can't simplify that initially, okay, and get a whole number as an exponent. So when you encounter something like this, you say, okay, I can't take the square root of all of this, but I at least want to break this up so that I can take the square root of part of it. So we just saw that we could take the square root of x to the 8th. So I claim I can rewrite x to the 9th as x to the 8th times x to the 1st power. Why? Because when you multiply two things with the same base, you add your exponents. Now what I can do is essentially use this property here. That's essentially saying, well, that's the square root of x to the 8th times the square root of x. We just saw the square root of x to the 8th is x to the 4th, and so this is our final answer. Okay? Now we can also do a similar thing with numbers. For example, what if I wanted to take the square root of 28? Well, that's not a perfect square, so we're not going to get a whole number. However, we can ask ourselves, okay, we can't take the square root of all of it, but is there at least some portion we can pull out of our parentheses? And I claim my answer is yes. So what you want to do in these situations is take whatever numbers under your radical and break it up into two different numbers, one of which that you can take the square root of. Okay? And I claim we can rewrite this as the square root of 4 times 7, which can be rewritten as the square root of 4 times the square root of 7. And we can take the square root of 4 to get 2 root 7. All right. So let's do this one then. What if I want to take the square root of 50 x to the 4th, y to the 6th, and z to the 11th? Okay, so what I'm going to do right now is just look underneath my radical, and I'm going to separate some things out. I'm going to separate out what I can take the square root of and what I cannot take the square root of. Okay? So 50 is not a perfect square. So just like with that square root we just did, I want to ask myself, is there a way I can break up 50 so that I can take the square root of part of it? And I claim yes, I can break it up as 25 times 2. Now I ask myself, can I take the square root of x to the 4th? And again, square root is 2, so essentially we're asking, are these guys divisible by 2? And yeah, I can take the square root of all of x to the 4th. And in fact, what I'm going to do is I'm going to break this up. The first portion is what I can take the square root of. The second portion is what's going to be left behind under my radical. Next, I can take the square root of all of y to the 6th. But I can't take the square root of all of z to the 11th, but I can take the square root of z to the 10th, and then I'm going to have another z left over. All right, let's go through it. Square root of 25 is 5. Okay, square root of x to the 4th, well, 4 divided by 2 is 2. The square root of y to the 6th, 6 divided by 2 is 3. The square root of z to the 10th, 10 divided by 2 is 5. And then I got my leftovers still inside my radical. All right, let's do this one. What if I have 48 u to the 10th, v to the 12th, and y to the 21st. Okay, again, I'm going to follow the same procedure. I'm going to separate out what I can take my square root of and what I cannot take my square root of. So 48, well, 48's not a perfect square. So I'm going to ask myself, well, what portion of 48 can I take the square root of? Now, the more familiar you are with these numbers, the quicker they'll come to you. But I claim that 48 is 16 times 3. And I can take the square root of 16. I can take the square root of all of u to the 10th. I can take the square root of all of v to the 12th. And I can take the square root of y to the 20th, and I'm going to have another y left over. Okay? Square root of 16 is 4. Square root of u to the 10th is u to the 5th. The square root of v to the 12th is v to the 6th. The square root of y to the 20th is y to the 10th. And I'm left with the times the square root of 3y. Okay. So let's just do a few more. What if I have 64 to the negative 3/2 power? Well, what would we do here? What we would do is say, oops, we got a negative exponent. We got to make him positive. So let's do that. The way we make him positive is bring him down to the denominator. All right, our next step is to say that's 1 over 64 to the 1/2 cubed. And I ask myself, well, what's 64 to the 1/2 power? In other words, what's the square root of 64? And that's 8. So then what we need to do is cube 8, and I claim we're going to get 1, over 512. Right? 8 squared is 64, and 64 times 8 is 512. All right. What about this one? What if I have negative 64 to the 3/2 power? Can I do this? Well, remember there's no parentheses here, so my exponent only applies to this number, 64, and then I have my negative sign hanging out in front. So, yes, we already evaluated what 64 to the 3/2 power is, but let us assume that we've never seen something like this before. The way we would write it is the negative hanging out in front, we would put 64 to the 1/2 power and then cubed. Again, the square root of 64 is 8, and 8 cubed is 512. On the other hand, what if I had this? What would this lead us to? Well, now, since I have parentheses, my exponent applies to absolutely everything inside. So I have negative 64 to the 1/2 power cubed. Okay? I'm asking myself, what's the square root of negative 64? And my answer here is that there's no real solution. Okay? Again, why is there no real solution? Because you can't take the square root of a negative number unless you're dealing with complex numbers. All right. Let's do a few more. What if I have this? X to the fourth, y to the negative second, and that whole thing is raised to the third power. Okay? Now the fun thing about our properties of exponents is we have a choice often which we do first. And the beautiful thing is it doesn't matter which one we do first, we'll get to the same place. What do I mean by that? Well, notice one thing that I could do is bring my exponent of 3 into both of my terms. Or the other thing that I could do first is get rid of my negative exponent. Again, it doesn't matter which way you go first, as long as you do them correctly. I'm going to bring in my exponent of 3 to both terms. So I claim I have x to the fourth cubed and y to the negative second cubed. When you raise something to a power, raise to another power, you multiply your exponents. So I have x to the 12th, y to the negative 6th. And now I just have to rewrite this so that I do not have a negative exponent. All right, I have 2 more that I would like to do. Actually 3 more, excuse me. What if I have, how about x squared y to the negative third over w to the fifth x and z to the negative fourth, and let me have a z up here too. Isn't this beautiful? And why don't we raise that to the negative second power? Just to make it look particularly nasty. Okay, again, I can proceed in a couple different ways. I could bring my exponent in first, but my own preference is to simplify what I have in my parentheses first. Okay, so what do I mean by that? Well, let's look at our x's. We have x squared over x. Notice when you divide 2 things with the same base, you subtract your exponents, and 2 minus 1 is 1. Okay? What else do I have? Well, this is my only y, so I'm just going to leave him as is. I know it's tempting to get rid of the negative exponent, but notice we have a negative exponent out here, so let's just leave that alone. So I've taken care of my x, my y. My w to the fifth stays put. Now I have z over z to the negative fourth. Probably what I would do there is, well, you could look at it as, well, when you divide 2 things with the same base, you subtract your exponents, and 1 minus a negative 4 is z to the fifth. Okay? Another alternative is you could say, ew, I got a negative exponent down in my denominator. Let's bring him up to the numerator to make him positive. And then I have z times z to the fourth, but that gives me z to the fifth. All right, now what I can do is bring my negative 2 into each of my variables. So I have x to the negative second, y to the negative third to the negative second, z to the fifth to the negative second, over w to the fifth to the negative second. Again, do these things step by step. Don't look at the big picture first. So I have x to the negative second, y to the sixth, z to the negative 10th, over w to the negative 10th. Well, My last step is just to make sure all my exponents are positive. X to the negative second, oops, got to bring them down. My y to the sixth is good where he's at. Here, let me move this over here. So x to the second, y to the sixth is good. I have a z to the negative 10th, so I got to bring him down to make him positive. And then I have a w to the negative 10th in my denominator, so I need to bring him up to make him positive. I know that's a lot of steps, but again, just do them one by one. All right, so two more that I would like to do. What if I have a to the n plus 1 times 3 to the n plus 1 divided by a to the n times 3 to the n? All right, well, notice no negative exponents. At least that's a positive, no pun intended. All right, but what I do have is I've got two things with the same base, one in my numerator, one in my denominator. So I know that when I'm dividing two things with the same base, I subtract my exponents. So I have a to the n plus first minus n. And I'm going to have the same thing with my 3. Well, n minus n goes away, so I'm just left with an a to the first times 3 to the first. Now, you can leave it like that. I'm just a little anal about things, and I like my numbers before I have my variables. Okay? All right, so the last exercise that we're going to do here is as follows. What we want to do is simplify as best we can a to the negative first plus b to the negative first, that whole thing raised to the negative first power. Now, wouldn't it be lovely if we could bring our negative exponent into each of those terms? Why can't we? Well, the reason why we can't is precisely because we're adding in here. So, there's a couple different ways we could look at this. Okay, one way we could look at this is that's 1 over a plus 1 over b to the negative first. I usually like to simplify what's in my parentheses. All right, well, look, I've got two fractions. What do you do with two fractions? You get a common denominator. What would the common denominator be here? Well, I have an a here and a b here, so I claim a times b would be my denominator. Well, I have the a here, so in order to get b in my denominator, I'll need to multiply and divide the first term by b over b. And in order to get an a in my denominator here, well, if I'm going to multiply my denominator by a, I've got to do the same thing with my numerator. So now I claim I have a common denominator of ab, and in my numerator I have b plus a. That whole thing is raised to the negative first power. Well, we can go over here to our properties of exponents, that when you have a over b to the negative nth power, that's the same as b over a to the positive nth power. In other words, I can write this as ab over a plus b to the first power. In other words, ab over a plus b. Wasn't too bad. I know it's not the prettiest thing we've ever seen. Okay? Now, if you're curious if you could address this negative exponent first, you absolutely can, and I highly encourage you to do that on your own, and you will see that we get to the exact same place. So, before you start lesson 4.1 in this chapter, I highly encourage you to do these skill refreshers in your book, and that's that. Thanks.